Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on the empirical rule. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint in making this set of videos. We will spend much of our time in statistics studying data that is normally distributed. This is our first introduction to the concept, and we will look at this graph that will represent normally distributed data. As we study the graph, notice its shape. We call the shape of this graph bell-shaped. It is symmetrical around this center line. That means it has the exact same shape and size on both sides of this line. This line represents the mean or the average of our data, and we will mark that with mu. Mu being the symbol for the population mean. The area under the curve represents the probabilities. What are the sum of our probabilities in any one problem? Well, that would be 1 or 100%. So the total area under the curve is 100% or 1. Since the mean is the center, that leaves 50% of the area on each side of the mean. 50% of the area is above the mean, and 50% of the data or area or probability is below the mean. Each curve is defined by its standard deviation. We will draw most of our curves to look the same and change the scale underneath. In other words, we are not interested in being totally accurate about our graphs. We are just drawing rough sketches, but we do want our numbers to be accurate even if the shape is not. So the mean always goes in the center. Then we have the first standard deviation jump, and we will make the jumps to the right first. This mark is important because it tells us about the spread of our data. The standard deviation is a measure of how far or how our data is spread out and is different for different data sets. Notice that we will indicate this with mu plus 1 sigma, or the mean plus 1 standard deviation. And if we had numbers here, we could calculate this value for this point, or we could label it as we have here, mu plus 1 standard deviation with our variables. Then we can have a second standard deviation jump, adding another standard deviation, and that would give us the mean plus 2 standard deviations, or mu plus 2 sigma. And we could do the mu, add another standard deviation or another sigma, and that would give us mu plus 3 sigma, or the mean plus 3 standard deviations. And that takes care of moving toward the right. We can also move toward the left by subtracting or going below the mean. And to move below the mean, we would subtract our standard deviation. When we subtract our standard deviation, that would be the mean minus 1 standard deviation, or mu minus 1 sigma. Again, doing a second jump or subtracting a second standard deviation would end up with mu minus 2 sigma, or the mean minus 2 standard deviations. And again, doing it the third time leaves us the mean minus 3 standard deviations. And we have labeled our graph. Notice how the curve has more data in the center and less toward what we will call the tails, which are the left and right hand sides of the graph. And we have fewer data and fewer area under the curve as we get further from the mean. And does that make sense to what we already know? If the mean height of a woman is, say, 5'2", that would be in the center where the mean is. Are there more women toward the center of this data than there would be, say, at 5'10" and 4'6", which would be further away from the data? And yes, there would be more women close to a center than out toward the ends. As we look at the graph, there are some things that mathematicians just know. First is about one standard deviation from the mean. We know that one standard deviation from the mean in either direction, we can make the statement that 68% of the data lie within that one standard deviation of the mean. In other words, this area within that one standard deviation incorporates 68% of the data. We know this from people a lot smarter than me, and we will use this to work some examples. Next, we will look at two standard deviations from the mean, two jumps in both directions. We know that 95% of the data lie within two standard deviations of the mean. 95%. Next, we look at three standard deviation jumps in both directions. 99.7% of the data lie within three standard deviations of the mean. This is essentially all of the data. Remember, bell-shaped curves theoretically go forever to the right and to the left, so it's not 100% of the data. There is the data that goes to infinity in both directions. This is called the empirical rule for normally distributed data. The empirical rule for normally distributed data simply states that we have 68% of the data within one standard deviation of the mean, 95% of the data lie within two standard deviations of the mean, and 99.7% of the data lie within three standard deviations of the mean. 68, 95, and 99.7% of the data lie within 1, 2, and 3 standard deviations of the mean. You will need to memorize these 3% and their corresponding standard deviations. I am going to conclude part 1 of this PowerPoint here, and we will pick up with an example in part 2.